In this video, we look at the energy levels and allowed transitions of the hydrogen atom, taking into account the spin-orbit coupling and an external magnetic field. First, let's neglect spin-orbit coupling. The energy level diagram of a hydrogen atom then looks like this. The 1s level is lowest energy. The 2s level and the 2p levels lie higher in energy, but they both are degenerate. This is the simple model that neglects spin-orbit coupling. Next, let's reintroduce spin-orbit coupling. The spin-orbit coupling leads to small energy shifts depending on the relative orientation between the spin and the orbital angular momentum of the electron. In the 1s and 2s states, the electron does not have an orbital angular momentum. Therefore, there is no spin-orbit coupling and the energies are unaffected. Using the term symbols, the 1s is a doublet s1/2 and the 2s is also a doublet s1/2. Now, in the 2p states, the electron has orbital angular momentum, L equals 1. When combined with the spin orbital angular momentum, we get the total angular momentum J. In terms of quantum numbers, J equals L plus or minus 1/2, where 1/2 stems from the quantum number S. So the total angular momentum quantum number J can be 1/2 or 3/2 if L equals 1. The relative orientation of spin and orbital angular momentum differ for the two J's. For J equals 1/2, they're parallel or antiparallel, and for J equals 3/2, they're parallel. Therefore, there's a slight difference in energy between the two sets of states. The set with lower energy has J equals 1/2 and is labeled a doublet P1/2, where the 1/2 stands for the J equals 1/2. The set with higher energies is the doublet P3/2, where the subscript 3/2 indicates the total J quantum number. The energy difference here is really small, whereas between the 1s and the 2s configurations, we have about 10.4 electron volts gap. The energy difference between the two doublet P states is only 0.045 milli-electron volts. Each of these levels contains several degenerate states. The levels with J equals 1/2, that is the 1s, the 2s, and the doublet P of the 2p, each have 2 states, and the level with J equals 3/2 has 4 states. This is the energy level diagram of the hydrogen atom, including the spin-orbit coupling. Next, let's place the hydrogen atom into an external magnetic field. As a consequence, the degeneracy of all the states within each level is lifted, and the energy is split. This is called the Zeeman splitting, or the Zeeman effect. The lower doublet S1/2 has 2 states, which have different energies in the magnetic field. So we get a splitting for the doublet S1/2, which stems from the 1s, and the MJ values are negative 1/2 for the lower one and positive 1/2 for the upper one. The 2s doublets S1/2 level also has J equals 1/2. So you again get a splitting into 2. 2s doublet S1/2. The doublet P level here also has J 1/2. So again, we have a splitting into 2. Doublet P 1/2 based on a 2p configuration. Lastly, the doublet P 3/2 has J equals 3/2. So there are 4 states which are now split in the magnetic field. 1, 2, 3, 4. The uppermost level has an MJ equal to plus 3/2, and the lowest one has an MJ equals to negative 3/2. So this is the quartet of levels for doublet P 3/2. This is the energy level diagram for a hydrogen atom, including the spin-orbit coupling and in a magnetic field. Next, let's look at the possible transitions between states. For the simple model on the left that neglects the spin-orbit coupling, the allowed transition is from 2p to 1s. For the full diagram in the middle, let's first write down the selection rules for the electronic transitions in atoms. There are 4 conditions that have to be met. The first 2 are rather strict. Delta L equals plus minus 1. the change in orbital angular momentum quantum number has to be 1. Second is delta S equals 0. The overall spin quantum number is not allowed to change. The second two conditions limit changes in the overall total angular momentum quantum numbers and are a little less strict. First, delta J equals 0 plus or minus 1. And then delta M sub J equals 0 plus or minus 1. Notice that we're using uppercase L, uppercase S, and uppercase J instead of lowercase l, lowercase s, and lowercase j. The uppercase letters are used for multi-electron atoms, and the lowercase is only valid for one-electron atoms. We wrote them with the uppercase letters to be more general, because these selection rules are also valid in multi-electron atoms. Now let's draw the transitions. The first selection rules limits us to two transitions. This and this. The spectrum consists of two lines. In a magnetic field, we get more transitions and lines. There is no restriction from the doublet P1/2 down to the doublet S1/2. So we get 4 allowed transitions from the upper level to the upper level, from the lower level to the upper level, from the upper level to the lower level, and from the lower level to the lower level. From the doublet P3/2, we have to make sure that the fourth rule about delta Mj is satisfied. For example, we can't go from the Mj equals plus 3/2 state, the top state, down to Mj equals -1/2, the lowest state, since the Mj will be changing by 2. So overall, we get 6 states. We can get out of the top 3 states all the way down into the Mj equals +1/2 state. And from the lower 3 states, we can reach down to the Mj equals -1/2 state. I'm not fully drawing the lines because otherwise the diagram would be too busy. So in total we get 6 transitions for this upper manifold and 4 for the lower manifold. That's a total of 10 transitions, and if you have a spectrometer that has sufficient resolution, you will observe 10 different lines. In summary, we have seen that spin-orbit coupling leads to a splitting of the 2p states into 2 groups, one with j equals 1/2 and one with j equals 3/2. The s states are unaffected. In a magnetic field, all levels split, and all degeneracies are removed. We also saw the selection rule, which has requirements for all 4 angular momentum quantum numbers, L, S, J, and Mj.